Okay, let's talk about isotopes. So, I mentioned isotopes with Dalton's atomic theory, that isotopes are how the part where Dalton proposed that atoms of a given element are identical in mass and behavior ended up not being true. So atoms of a given element are going to be identical in behavior because to change the element, I have to change the number of protons. So if I have 6 protons, I have one element. If I have 7 protons, I have another element. However, if I have 6 neutrons, I could have that with my 6 proton element or my 7 proton element. Okay, and so the mass of an element has to do with the protons and the neutrons. So if you remember when we looked at the relative masses of protons, neutrons, and electrons, the mass is contained within the protons and the neutrons. And so if I mix up the number of neutrons, I can mix up the mass. So when we look at our isotopes, okay, so basically the definition of an isotope, atoms which differ only in the number of neutrons present in the nucleus. So atoms of an element identical in atomic number, but not in mass number. Neutrons are going to kind of keep that atom together by buffering that strong nuclear force without adding to the fact that if I have a positive charge and I have a positive charge, we know those repel each other. And so we have these neutral neutrons that are peppered throughout there that help hold everything together. They're kind of like our atomic glue, our nuclear glue. All right. Typically speaking, we have 1 to 1.5 neutrons per proton in the nucleus of an atom. When we look at nuclear chemistry, we can talk about something called the band of nuclear stability, which helps us determine whether or not we're going to find a 1-to-1 ratio, a 1.25 to 1 ratio, a 1.5 to 1 ratio. It kind of differs as we go throughout the periodic table. All right, so hydrogen. Most of hydrogen is only a proton, which is why if we have an H plus ion where we've lost 1 electron, we just call it a proton because that's all that's left. So I can write some symbols here for my isotopes of hydrogen. Now hydrogen's a really interesting case because it's so simple. It's just that single proton, single electron for the vast majority of the isotopes. And then we've got some where we've got some neutrons added in there. So hydrogen's the only one where we have specific names for its isotopes. Most of the time we just say something like carbon 12 or carbon 13. But hydrogen, we have protium, a mass number of 1. So I can write a symbol for hydrogen that looks like this. Okay? So protium is also known as hydrogen 1. Okay? Deuterium, I'm going to make a symbol that looks like this. Okay? I can also call that hydrogen 2. And then tritium, I can make a symbol that looks like this. I can also call that hydrogen 3. So the way this works is the number that is superscripted in the upper left-hand corner, that is what is known as the mass number. That is going to be comprised of the protons plus the neutrons. The number in the bottom left-hand corner, that is the atomic number. That's simply the number of protons. Now, if I pick up a periodic table, so if you're, concurrently enrolled in the lab, you should have a periodic table that looks like this in the lab manual. And I can look on here, and above hydrogen, centered, is a number 1. That is the atomic number. So I can look at the periodic table and get my atomic numbers. Okay, so as long as I know the identity of the element, I can look at the periodic table and figure out what the atomic number is, how many protons it has. If I know the atomic number, I can look at the periodic table and figure out the identity of that element. Okay, and so we've got these symbols where we've got our mass number, our atomic number, and then the symbol of the element. Okay, and so whatever the mass number is, that's the isotope. So again, with carbon, if I have a carbon with a mass number of 12, I call that carbon 12. If I have carbon with a mass number of 13, I call that carbon 13. Okay? I can't tell how many isotopes something is going to have just by looking at the periodic table. That has to be done experimentally. So something like magnesium. Okay, magnesium has 3 naturally occurring isotopes: magnesium 24, magnesium 25, and magnesium 26. So all 3 isotopes of magnesium are going to have an atomic number of 12. Okay, And then when I go through and I look at their mass numbers, 24, 25, and 26, well, if the mass number is the protons plus the neutrons, all right, mass number 24, 24 minus 12 protons gives me 12 neutrons. Okay, 25 as my mass number, well, 25 mass number minus 12 protons gives me 13 neutrons. And then magnesium 26, subtract off that 12, and I have 14 neutrons. Now, one thing to notice is, if you look here in this row, okay, well, it just flipped on me, but if you looked on that row, you would have seen that it had the same number of electrons. So atoms in their natural state, they are neutral. And so since protons and electrons are opposite charges, for a neutral atom, my number of protons will equal my number of electrons. When I have an ion, that's when I have to add or subtract electrons. I'm only adding or subtracting electrons. Okay, here's some illustrations of sodium 23 and silver 109. So sodium 23, I have 11 protons. So 23 minus 11 is how I get my 12 neutrons. And then I would have 11 electrons to balance off the 11 protons. Silver 109, 109 minus 47 gives me my 62 neutrons. And then 47 protons, I have 47 electrons to make it neutral. All right, so here's one. All right, now let's figure out what element this is. So I have some clues on here. I have 30 neutrons, I have 25 protons, and 25 electrons. So remember, the number of protons is the atomic number. So that's where I'm going to go over to my periodic table. And I'm going to take a look. All right, I'm going to look for number 25. The element with atomic number 25 is manganese. So this element is manganese. Okay, what particular isotope is it? Well, for the mass number, we'll add the protons and neutrons together. So 30 plus 25 gives us 55. So this is a manganese 55. So I can write it like this. Okay, so there's my manganese 55. Okay, here's another example. Now, I've used Q as my unknown element here because there is no element on the periodic table that has a symbol of Q. So you have to look at those numbers. Okay, so my first example, I have some element 11. So I have 5 protons because that's shown there. I have 11 over 5. So my atomic number is 5. So my protons is 5. So my neutrons, I'm going to take 11 minus 5. Okay, so I'm going to get 6. Okay, neutral species. See, notice there's just Q. There's no ion charge there. So no ion equals neutral equals protons equals electrons. Okay, so if I have 5 protons, I would have 5 electrons. All right, now to figure out the element, again, I go to my trusty periodic table, I look and I go, oh, element number 5 is boron. Okay. All right, next up, I have a mass number of 41 and an atomic number of 20. So atomic number is number of protons, so I fill that in. Still neutral, so my electrons is also 20. Okay. Then I go to my periodic table and I go element 20. Oh, that's calcium. I'm so used to writing the abbreviation for California. That's better. Okay. All right. My last one. I have a mass number of 131 and an atomic number of 53. So atomic number of 53 means I have 53 protons. My number of neutrons, I'm going to take my 131 minus 53, and I'm going to get 78. Okay. Once again, I go to my periodic table, and I look for 53, and I find that that is iodine. Okay, so I can get my number of protons, my atomic number from the periodic table. I cannot get my number of neutrons though. The masses on the periodic table are actually weighted averages. So when we looked at that magnesium, there are some percentages on there. And that's what we're going to talk about next, is atomic mass and how we figure out what those numbers on the periodic table are. Because if you look at them, most of those are decimal numbers. They're not whole numbers like the mass numbers that we've been dealing with here. Okay, so we have one more example, and then we'll take a look at atomic mass. Okay, and so for our isotopes of carbon, so here again, I've got those percentages. Okay, so percent abundance basically means that in a sample of carbon, 98.89% of it is going to have a mass number of 12. So the vast majority of carbon is carbon 12. There's not a whole lot of carbon 13 or carbon 14 out there. Okay, 1.11% is carbon 13, and only 0.01% is carbon 14. So if you look on the periodic table, the mass of carbon you'll see is 12.01. And that's because you have contributions from the carbon 13 and the carbon 14. Carbon 14 is cool. That is actually radioactive. So carbon 14 is how we do carbon dating. Okay, so we can write these symbols, our carbon 12, our carbon 13, and I'll write carbon 14 under here because I couldn't adjust this to not have the little video feed there. Okay, so that's how we write the symbols. And then now we'll take a look at that atomic mass in our next video.